Thanks. Thank you for the introduction. Hi, everyone. It's really great to be here. So today I'll talk about processing data with nanoscale memristors. We heard a bit about memristors and ReRAM and emerging technologies yesterday in one of the morning talks. So we all know also about the famous lecture by Feynman in a few decades ago, where he introduced effectively the possibilities that nanotechnologies offer to us. And in his famous lecture that there is plenty of room at the bottom. So his prophecy basically has been partially fulfilled, because although we have access to all these fantastic capabilities for controlling matter at nanometer scale, we are actually failing to do this reliably. And as we're going further down in scaling, we're observing a big variation in switching threshold, for example, of these devices due to this random fluctuation in dopant location and concentration. But our community is greedy for innovation, and we want more and more. And we know so far we've been exploiting this fantastic scaling opportunity that Moore's law has given us for improving computation, but effectively we're going to hit a wall here. So I said that our society is greedy, and we heard this so many times in these talks over this summit. We want more data, whether it's voice or data over the internet. We want more devices to be interconnected. And even going into a very different topic, scaling of these more, if you like, principle goes also for biological systems, where we want actually to be able to record more neurons effectively in bioelectronic systems. So let me just give you an example of what kind of challenges we have by doing so. So if we want to process in real time at large scale neural activity, we have to deal with something that looks like that. And to put it in an analogy, it's like having an amphitheater full of people. And you are all basically representing one neuron in this array. And what I'm trying to do is I'm trying to capture your voices, who are giving the specific activity and the specific signature of each one of you. And that's the sound, effectively. And this represents the activity of the neurons. And the way to do that is by having some microphones. Well, here we have the luxury of having some mobile microphones that we can give around, and then you can start asking questions, and we can all listen to you. But when you are in something like that, in an implanted system, for example, this have to be in a fixed location. So it's like I would have to distribute 1,000 microphones around in order to make sure that I capture every single voice that can exist in the room. And in order to process that, I will need a sound console that will be able to process all of these in parallel simultaneously. This is impossible, obviously, even for microphones, because we have issues with power, bandwidth, area, and complexity. And the alternative approach that we want to give is that we need to basically do some pre-processing, on-node processing, where we detect all of this data by embedding some local capability that can detect, process, and store this information very efficiently. To put it in an analogy, is like what the human retina basically does. We receive so much information coming through our eyes every single second. But if we were to transmit all of this data through the optical nerve, simply we don't have the capacity to store all of that and to process all of that. So the retina, which is also known as the only part of the brain that sticks out of the head, is able to pre-process all this information locally and then send only something relevant to our brain for further processing. For example, I'm looking at Jeff. I know that is Jeff because I know him very well. But if suddenly Jeff was coming in with his hair painted pink, that immediately will raise a flag to me. And that's something that our brain processes. So coming to the underpinning technology, memristive devices, the chap on the left, Leon Chua, who is considered as the father of this concept, back in 1971 at UC Berkeley, he came up with the concept of memory resistors, simply from a theoretical argument by looking at what could actually, from a symmetry argument, that there should be basically a component linking charge with flux, as we have, for example, a resistor linking voltage with current. And he coined that element as the memory resistor and short memristor. And in 2008, the chap on the right, Stanley Williams, he was working in Hewlett-Packard Labs, into terminal titanium oxide resistive RAM devices. His success was that he managed to correlate the dynamics of these devices with a theory presented by Chu about 40 years ago. In a famous paper that is well cited these days in Nature, we found the missing memristor. And effectively what the signature of these devices is in the current voltage domain when they are excited by a periodic signal is a pinch hysteresis loop that looks like that. And this inertia nonetheless exists everywhere, naturally in nature. So it's not something really new. How many of you know this person here, Humphrey Davy? Maybe some of you already heard my talk. How many of you know Faraday? I will be surprised if you don't know Faraday. Right, so this chap here was lucky to be around in the 1800s, and he was a director of the Royal Institution. And he was lucky to be around when Volta discovered the voltaic pile. And he took basically the voltaic pile, stuck it up in series, and realized that he can do some very interesting things, build large potential. And because of that, he managed to demonstrate three things. Electrolysis, stimulate the legs of a dead frog for the first time, and also bringing two carbon electrodes in good proximity and succeeding in seeing the first artificially ever made light but through discharge. So that was named back then the electric arc, and followed up into the discharge tubes that all of them actually follow this, have this inertia, this signature of a pinch hysteresis loop. Is an interesting story behind this is that although at that time France was in war with England, Napoleon was a big fan of scientific discoveries. So although they were in war, he sneaked a secret passport to him with some money to get him in Paris to give some talks and excite, like the community in Paris. And the money that he also sent him to was to assist him with his travel, and it was basically to get a servant to help him with his trip. And that servant effectively was Faraday. So this chap was Faraday's supervisor, and he was considered as the one who developed, if you like, the first ever made memristor 2 centuries ago. And there is a nice commentary story in Nature Materials that you can read about this. So if this is about 2 centuries old, why should we actually care these days? We should actually care because these technologies, when considered at the nanometer scale, can achieve more for less. And of course, as with any technology, and we heard about quantum before, every single emerging technology follows the hype curve. So there is loads of excitement in the beginning, and then reality kicks in, and we have to face that, we have to do something about this. It's not as nice as we thought it would be originally. And with a lot of work and hard developments, and hopefully some research funding, we can do something, realistic. So I can point every single point for this technology. Functionality, so the devices can demonstrate not just, it can be used not just in a binary mode, but they can support a multitude of resistive states. Footprint, smallest device ever reported up to date is about 8 by 8 nanometers, and they're still scaling down. Power, you only need a picojoules or femtojoules of power to toggle between resistive states, and you can do that even with picoseconds of pulses. The ugly stuff is that this is not an excuse. I mean, they're not an excuse to the rule. With the scaling, you also have big variability with these devices as well. Stochasticity, other issues that need to be sort of addressed. But of course, we have a lot of know-how from other technologies. Wasn't it exactly the same with other memory technologies, like with flash, etc.? And there is a lot of know-how that we can use with, for example, some feedback mechanism that we can exploit for getting some compromise. And whenever something doesn't work, everyone argues that this is either good for neuromorphic technologies or for sensors. And that's exactly what I'm going to tell you today. So it's not difficult to fabricate these devices. As I said, inertia exists anywhere in nature, so it's the most natural thing to have. Therefore, everything switches. What you see in a color-coded map here is basically reports exist in the literature that they have demonstrated this resistive switching with memristors. We're more interested, however, from a technological point of view of integrating this with CMOS technologies so that we can leverage all the multi-trillion investment and development that these mature technologies have. And therefore, my group focuses mainly at developing tungsten oxide, tantalum oxide, hafnium oxide, silicon oxide memory devices, as well as titanium niobium. So we do that at the fantastic cleanroom capabilities that we have at Southampton, which is a £250 million investment, and it's one of the few academic-based clean rooms that allows to do full post-processing of any technologies at 8-inch wafers. So we take full CMOS wafers and we post-process. We have the capability to post-process these technologies at top, either in a single devices format or in a cross-bar configuration. And one of the state-of-art that we demonstrated, as I said earlier, the smallest device ever reported is about 8 by 8 nanometers, but this is single devices. And of course, tessellating that in a crossbar array is a different challenge. So what we demonstrated in my group is just last year, is about 1.5 by 1.5 micrometers, where you have a 1 kilobit array, which is functional. And to the best of my knowledge, this is the state of art in terms of density reported of these devices so far, even in an academic clean room. There are some talks tomorrow as well on alternative technologies, flexible, printed, and all of that. So it's very interesting to say that all of these technologies require relatively low temperature budgets for manufacturing, which is great because A, we can post-process them at top of CMOS technologies on back of the end without compromising our CMOS infrastructure. B, we can integrate them even in flexible formats, and we can stretch them. We can do whatever we think it's interesting to do with these kind of technologies, and they do work for thousands of cycles. So what really makes them unique for processing data? This is another state of art that we've demonstrated in my group very recently. I'm really, really proud of this work because we've demonstrated up to 7 bits of states per single device. So do the maths, see how much savings you can actually have in terms of the scaling. That's why we argue more for less. And this is the median response that we get in a 1 kilobit array, which is about 5.5 bits, and it keeps improving, and they're all discernible resistive states. You would argue that whether these are truly discernible, especially over time. These are non-volatile technologies. So we've also looked at some closely packed states, run retention for more than 8 hours, and they are indeed discernible, and they do remain there. There is some clever engineering behind the materials that we've used in the stacks, but again, we used standard materials, so there's nothing really complicated there. And the beauty of this is, of course, that you can use it as a tunable load, and you can arbitrarily program it to whatever resistive stage you wish, very nicely and relatively reliably compared to what we were a couple of years ago. So there is indeed progress in this area. And of course, you can do that with only picojoules of energy required. So first example I'm going to show you how we can use that for processing big data is these devices effectively. These blocks show a number of a train of pulses for programming the devices, and these 2 bands indicate the switching thresholds of the devices that they have. Intrinsic switching threshold a single nanometer scale device has. So if you stimulate it, of course, below the switching threshold, nothing happens to its resistive state. Once you exceed that, effectively you start observing these analog waves, which are non-volatile. And that's great because you have a nanometer scale device that intrinsically can act as a thresholded integrator. And once you're operating above that, you can then use it as an ideal integrator effectively. So effectively, devices act like that. Nothing happens in here, and you have changes in the resistive state outside these bands. And we've used that with biosignals, which actually carry a lot of, there are very, very rich signals. And we simply, these are real data, all of the measured data. And once you actually exceed the switching thresholds of these spiking events, you transduce that in a non-volatile change in the resistance of your devices. The beauty there is that you don't need to oversample, so you can go back and check, at any time what is the overall activity that you have actually monitored at that location. And we benchmarked that with against the more complicated template matching, which are very computationally expensive to run. techniques, and we had very, very good agreement with our measure results, and it was published. This work was published last year. We tessellated that in a larger array, so we can actually monitor at larger scale a number of neurons being active on top of this. And overall, that shows we've demonstrated about a 2 to 3 orders of magnitude improvement in power from the state of art that existed in the literature. Of course, there are bad news there, because the devices also do saturate effectively, and you might need to do some frequent resets. Nonetheless, there are some opportunities there, because if you start operating the devices at a particular region, you can exploit volatile effects as well to allow for the device to reset by itself. And therefore, you have extra power savings because of that. Switching gears to the second example of how you can actually process big data with these devices. This was published again last year in this journal, and we basically use the intrinsic property of the devices, that the corresponding change in the resistance that you have by programming these devices depends entirely on what the initial state of the devices are. So if you are in a low conductance state and you're trying to push it in a higher conductance, it will be easy, and vice versa. And we use that with this way of programming, so that we basically can achieve a depression, a potentiation, or a neutral area. And without training the network effectively, or training the devices, we can encode these conditional probabilities of a range of a pre or post events, so potentiating or depressing events, and depending on the number of these events, we can encode that into the change in the resistance of these devices. Because I'm running out of time, I'm just going to go quickly to the application, which is when you put it in a Winner-Take all network, you can actually start looking at specializing these devices at specific features. And the beauty is, because it's done in an unsupervised learning, so we haven't really trained it, you can see immediately this being applicable for embedded kind of applications, where any signals coming in, your network can actually learn how the different class centers move around, and you can have a variable, basically a classifier like that. Just as inspired by a presentation that I saw yesterday about the Internet of Everything, just as a teaser, as a last slide, I just want to show you some great work that we did through a European project called romped that finished about a few months ago, where we basically integrated these capabilities even across geographical boundaries. So this is the very first of the time that I'm aware of that someone has actually linked real neurons through memristive devices as synapses to artificial VLSI neurons, and then getting the response of that and feeding it back as well. And of course, on top of everything, we've actually done that across Europe without having to leave the luxury of our laboratories at Southampton or at Padova or at the Institute of Neuroinformatics at Zurich. So watch the space. This is some really cool work that I'm hoping that maybe next year, if we are all okay, we'll be here and we can give you more information about that. So to conclude, I hope that I convinced you that Memristors actually offers some unique solutions for processing big data, especially for the emerging area of the Internet of Things. And this technology also offers a lot of opportunities for implementing advanced machine learning techniques in silico for the first time without compromising biological fidelity, and especially for the elements that are required to have in the most numerous which are synaptic connections. And I'd like to close also with another quote by Feynman, as I started, who said that what I cannot create, I do not understand. So hopefully we should be able, in principle, our vision is in the future, to be able to use these technologies for even emulating disorders in the brain and different conditions in silico and testing that there. Last but not least, of course, this is not my work. It's thanks to this fantastic team And Alex has been responsible for the unsupervised learning part in the circuitry. He's developed the biosensor concepts, and Ali is responsible for fabrication of the devices. And our collaborators at TU Graz, Padova, and Max Institute, and Giacomo Indiveri at the Institute of Neuroinformatics. And of course, without the support of these projects that actually all of them finished recently, besides one, we will not be able to show this work. So thank you very much.